Hello everyone and welcome to our paper, Deploying Secure Distributed Systems, a Comparative Analysis of GNS3 and SEED Internet Emulator, which has recently been submitted and accepted to MDPI's Journal of Cybersecurity and Privacy. The co-authors are as follows. It's me, Lewis Golightly, as the leading author, Paolo Modesti and Victor Chang in Teesside University and also Aston University. So this paper in the empirical results will directly contribute to my study of the PhD, the Doctor of Philosophy in Computer Science. So network emulation offers a flexible solution for network deployment and operations by leveraging software to consolidate all nodes in the topology and utilizing the resources of a single host system server. So the study investigated the state of cybersecurity in virtualized systems, covering vulnerabilities, exploitation techniques, remediation methods, and deployment strategies based on an extensive review of the related literature. So we conducted a comprehensive performance evaluation and comparison of two network emulation platforms, which is Graphical Network Simulator-3 or GNS3, an established open source platform, and the SEED Internet Emulator, which is a current emerging platform alongside physical Cisco routers and technology. So additionally, we presented a distributed system that seamlessly integrates network architecture and emulation capabilities by combining GNS3 with physical Cisco nodes to see how they perform together. So the empirical experiments assess various performance criteria, including the bandwidth, throughput, latency, and jitter. Insights into the advantages, challenges, and limitations of each platform are provided based on the performance evaluation. And we analyze the deployment costs and energy consumption, focusing on the economic aspects of the proposed application. So the motivations driving this research include the investigation of how network emulation and hybrid systems can provide advanced control and flexibility when integrated with existing infrastructure, enabling organizations to adapt to changing business needs and network demands, and to explore the ability to use network emulation and hybrid systems for offering cost-effective and efficient solutions for businesses, particularly focusing on small and medium enterprises by combining existing physical infrastructure with an emulation-based architecture. So in the study, we presented the experimental results of a proof of concept network and analyzed the performance of various solutions, including physical Cisco infrastructure, emulated GNS3 and SEED Internet Emulator, and a hybrid network model combining GNS3 with the Cisco technology. We begin by conducting comparative testings of the performance between GNS3 and SEED Internet Emulator based on predefined performance criteria, which is the bandwidth, latency, throughput, as well as energy consumption. The hybrid system is developed by integrating the physical Cisco devices and GNS3 appliances, enabling us to evaluate the performance and quality of the hybrid emulation integration through similar experiments. Finally, we assess the economic benefits of a specific network implementation and energy consumption and cost, with the main contributions of our research being to provide a comprehensive analysis of cybersecurity and virtualization technology, networking and hybrid systems, which include cryptographic mechanisms and security evaluation through an exploration of evidence-based related literature, which can be highlighted in section 2. We conduct a performance comparison of network emulation systems and a hybrid system, considering specific benchmarks such as bandwidth, latency, throughput, and other relevant metrics, which can be highlighted in section 5, as well as evaluating the energy consumption and cost effectiveness through data analysis and addressing the reliability and usability considerations around the platform, which can be highlighted in section 6. So we analyzed the deployment and application of a hybrid emulation system, combining Cisco infrastructure with the emulated GNS3 components and appliances, and conveying an evaluation including the identification of strengths, challenges, and notable findings of hybrid emulation, which can be highlighted in section 4, as well as providing specific recommendations for its implementation and optimization, and further enhancements, which can be seen in section 6. So the methodology for this study included a literature review, so a review on similar solutions. This is reviewing literature around GNS3 performance comparison evaluations, as well as normal Cisco traditional infrastructure. However, there was no literature that was found on comparing SEED Internet Emulator empirically to another network technology, so that was sort of the gap in the market for this paper. The network design, so the building and configuring of physical emulated and hybrid network models, the data collection using automated scripts, so TCL scripts for the Cisco appliances, and for loop for the SEED Internet Emulator. So the energy cost analysis, so measuring energy consumption and performing cost analysis based on the overall cost of the system. So for example, GNS3 has different costs to SEED Internet Emulator, as GNS3 uses Cisco devices. So there is an inherent cost in purchasing the appliances in GNS3, whereas in SEED Internet Emulator, it just uses a sort of Kali Linux-based host. So the network comparison compares all network platforms against predefined criteria. So we focus on bandwidth, throughput, latency, jitter, and energy consumption to base our comparison, and we provide evaluation and recommendations based on the architecture and the results that were found. So our literature review focused on vulnerabilities, exploitation, remediation, emulation, and virtualized network systems. So PSL discussed security issues in virtualization, highlighting the significant risk of implicit trust placed in virtual machines or VMs. So they also emphasized the dangers associated with VM cloning, stressing the importance of accounting for all VM instances to ensure security, and additionally, the abstraction of VMs from the underlying hardware, which can introduce vulnerabilities that can be exploited by cyber threats. So Wu-et-al. Investigated vulnerabilities in the virtualized computer network, particularly in the breach of isolation that allows the VM to monitor and access other VMs and the host machine. They also identified a denial of service or DOS vulnerability from the sharing of resources, including CPU, memory, disk, and network between the VM and the host. Hyde and Doug highlighted the emergence of new DOS attack vector and virtualization technology, particularly in cases where excessive resource allocation to a VM has been permitted. These such attacks can lead to the crash of the physical machine, host, and the hypervisor in the further VM files. Astrobacy focused on the cross-VM side channel attack that exploits vulnerabilities in VMs. They identified the specific attack types, including VM hopping, which results in denial of service by making resources unavailable to the user, VM escape, enabling guest-level VM to attack itself, and VM mobility, which allows the VM to move between physical hosts. So Brooks et al. Addressed security risks in cloud computing, including exploitation techniques such as footprinting to analyze the operating system platform remotely, botnets for DOS or denial of distributed denial of service attacks on virtualized systems, traversal attacks that compromise the data integrity by modifying the VM library contents, malicious code injection through man-in-the-middle attacks or redirection of communication with a virtualized management agent on the host platform. So the performance comparison criteria includes bandwidth, which is the maximum amount of data can be transmitted over a connection within a specific time frame, measured in bits per second or BPS. It is often referred to as the pipe width for internet traffic. Throughput, which is the rate at which data is actually transmitted over a connection, so measured by dividing the amount of information successfully delivered to the destination over a specific time by the duration of the time interval. Latency, which is the time it takes for data to travel from the sender to the destination across the network, which is measured in seconds. So the overall latency consists of three components, which includes propagation, transmission, and queuing. So propagation is the time it takes for the signal to travel from the sender to the receiver, and is a function of the distance between the endpoints and the speed in a given communication medium. Transmission is the delay that considers the actual size of data that is available to the bandwidth. And queuing delay considers the time waiting for packets before they can be transmitted. So jitter is the variation in packet delay at the receiver end of the communication, and it's computed by measuring n samples of ping time between two endpoints and computing the difference between the individual pings and the average value. So as every packet can be routed to different paths to reach the destination, jitter measures the consistency in the transmission delay, so therefore the lower jitter values are preferred. So energy consumption is calculated as the product of the power in watts and the time of use in hours divided by 1,000 to then obtain kilowatts. So in our evaluation between GNS3 and SEED Internet Emulator, when we compare latency in jitter in milliseconds, we can see that SEED Internet Emulator considerably outperforms GNS3 by having a significantly lower value throughout the max, min, average, standard deviation, median, and jitter. We can see that it's got a significantly lower value. However, the technology is extremely lighter weight than GNS3. So with the distributed system results, if we look again at the latency and jitter measured in milliseconds, we can see that the average results in here were reasonable. They were reasonable results, with the highest result being around 65 and going all the way down into the 20s. So we can see that these results are reasonable, and what this actually tells us is that combining network emulation and traditional technology that will be deployed in businesses and that's physical, it is possible to combine, and as we develop these technologies, start introducing hybrid solutions in for whatever use case that the business may have. And that was what we were thinking as well, by investigating into cost efficiency, by seeing, is it more cost efficient to add to physical infrastructure by adding in emulated infrastructure, or is there a use case where emulated infrastructure is suffice rather than needing to buy expensive physical infrastructure that has a lot of hidden expenses in there as well, in terms of having room to store it, all the way to repairs, replacements, and keeping it going in terms of cabling and things like that. So we can see with the bandwidth and the throughput, SEED Internet Emulator significantly outperforms GNS3 and the hybrid solution as well. But it is worth noting that it is significantly more lightweight than GNS3 is. So the benefits of adoption then. So we first got cost effectiveness. So network emulation allows businesses to create virtual network environments, so reducing the need for expensive physical hardware. It enables cost saving on hardware procurement, maintenance, and operational expenses. Flexibility and scalability. So emulated networks are highly flexible and scalable, allowing businesses to quickly adapt to changing network demands and requirements. So it does become easier to test and deploy new network configurations without disruption of the production network. Free risk testing. So emulated networks can provide an isolated environment for testing new applications, updates, and configurations before implementation in a live production environment. This can reduce the chance of network downtime or critical errors during the deployment. Test recovery testing and redundancy. So by providing an isolated environment, emulation allows businesses to test redundancy and disaster recovery strategies without affecting the live network that's in operation. And you can do this to ensure business continuity going forward. So network emulation fosters the collaboration between development and operations teams by providing a shared environment, which can be used for collaboration in testing and troubleshooting, and it encourages agile development practices and seamless integration of networks and applications. So energy efficiency is also improved. So emulated networks consume less energy compared to physical hardware, which contributes to reducing the carbon footprint and environmental sustainability in businesses. And by leveraging these benefits, they can enhance their network operations, reduce costs, mitigate risks, and get a competitive edge in a dynamic market landscape. So when doing the test for the energy consumption, we can first see in figure 6, the topology to the right, where we can see the national power grid, and the energy consumption measuring device when plugged into the wall goes into a power adapter that has up to 12 outputs. So this is how we measure fairly the outputs for the physical network, consisting of 6 nodes. We can see we've got the server on there as well, which hosts GNS3 and the SEED Internet Emulator platform. And we've got 3 distinct cables, such as an Ethernet cable, a power cable, and a console cable, so we can see how they fit into the network. When looking at the energy consumption table, we can see that SEED Internet Emulator, again, significantly outperforms GNS3 and the distributed system and the physical devices, which is a current trend within this study. So in the study, by conducting a comparison between the 2 emerging network platforms, the GNS3 and SEED Internet Emulator, our evaluation focused on the performance criteria, such as the bandwidth, throughput, latency, jitter, and energy efficiency. And while both platforms share a common concept, they differ significantly in terms of design, development, and execution. Through the research section, 2 and 6 are linked to the first research contribution, which highlights related literature, studies around virtualization technology, networking, and cybersecurity applications. Section 5 and 6 are linked to the second research contribution, which demonstrates the network performance comparison of the systems. Section 4 demonstrates the third research contribution, showcasing the network models under test. GNS3 being more heavyweight, offering greater integration flexibility, mimicking the typical network environment, and facilitating easy connections of external nodes and services from a variety of different vendors. So conversely, SEED Internet Emulator is more lightweight, flexible, and efficient in its development approach. By exploring the integration of network emulation platforms into the data center architecture and creating a hybrid emulation system, we utilize the SEED Internet Emulator and GNS3 to emulate networks using the host system resources. So our results indicated that while GNS3 possesses certain advantages to the platform, there are notable bottlenecks to consider when incorporating it into a company's infrastructure strategy. So GNS3 encounters issues with lower bandwidths and throughput speeds, and even with the internet service provider allows for higher speeds. So additionally, due to the platform's nature and its method for achieving network emulation, one of the main drawbacks is the challenge associated with allocating a large number of CPU cores to network appliances. And when CPU cores run out, it creates a bottleneck with the network appliances with you not being able to add more network appliances to that topology. So our observations revealed that the high energy consumption of the whole system poses a significant constraint to energy efficiency, which should be considered during the design phase. Our study demonstrated that for small networks, the energy consumption of the whole system alone can outweigh the physical energy consumption, and SEED Internet Emulator provides a lightweight emulation platform that exhibits flexibility in the development and performs impressively across all our performance criteria in the study. Here we can see the Python code used to build our Internet Emulator and our SEED Internet Emulator topology. So we can see that we first imported the libraries, we then used the services, so we created the services, OSPF especially. We can see here we then created the networks or the subnets for the routers to connect to. We created the routers and attached them to the subnets, and then we compiled using Docker for the emulation. So if you enjoyed this video and you think the study is relevant to you, please consider reading, citing, sharing, and recommending. It takes a significant quantity of time, effort, and collaboration to produce publishable scientific material, and this study in particular took over a year to produce. The reasons to cite, if you're writing research papers, can be around general computer networking, network security, platforms for testing, penetration testing and ethical hacking, or implementing interesting technologies such as blockchain or novel access control solutions. For other papers, please look at my research gates, the link is below. And there was a paper that was created before this, which follows the same sort of pattern as this paper. It's a survey paper, but it's around securing distributed systems and how access control can be embedded into interesting technologies such as SDN, network emulation, blockchain, and IoT. Thank you for watching. Thank you.